Okay, let's see. Um, Good morning. So, pretty small crew in the morning, but that's okay. I think it's kind of not to be unexpected with the 8 a.m. stream. It's kind of good. We'll be able to have a little more of a conversation since it's a small group. A couple administrative issues that I wanted to mention. Um, so we had finished up with chapter 6, gravity, last time. Uh, so that was there was a lot going on with that, including some kind of theory concepts and some ideas that we didn't have time to get to in the end of the chapter. So if you guys have any questions about any of that, please let me know. I'm not going to test you on things that we didn't talk about, but there's some really neat ideas in there, and if you've been looking at that and you're curious to learn more about it, let me know, and we can have a discussion, for example, on Teams or something. Um, but we're transitioning from gravity. Remember, that was a heavy vector-related idea, as was Newton's laws, and we're transitioning into thinking about more of a scalar quantity, which is energy. And the idea that we're going to get into today is work. And this is a concept that, um, it's similar to something like force. We have notions of what it means, but it also has a specific definition in physics. And so we're going to work on pinning that down, what it means, how you calculate it, etc. Today. Before we jump into that, though, a couple things I wanted to mention. So I've got a lot of grading to do, so I'm not gonna have a quiz on gravity until at least the end of the week, or early next week, because I want us to have a chance to talk about any issues with previous stuff before assessing on that. So that'll come eventually. Um, let's see. There were some questions about quiz correction grades showing up in the gradebook and counting as zero. That's a glitch with the gradebook. I've fixed it, but I'm not sure if it's going to stick, so I'll watch that. But in any case, don't worry about that. I have it on my list of things to pay attention to, so I'll get it straightened out one way or the other. It has to do with the way that the homework system talks to the gradebook in Blackboard, so I'm aware of it. That said, if you notice any other issues with the gradebook, things like, hey, especially between the homework system and the gradebook in Blackboard, let me know and I'll get them tracked down. Both It's kind of a combination of both of those systems being not that great, and then they're supposed to talk to each other, and the result is that it kind of doesn't work that well. So it's not anything that can't be fixed, but sometimes I won't notice. There's been some kind of mysterious errors where like only a few grades were omitted uh, in on Blackbird, but they were showing up in the homework system and other kind of weird gremlins like that. So if you notice something like that, bring it to my attention, and I'll make sure to pay attention to it. Um, let's see. Uh, Another issue between the homework system and Blackboard, or something that I wanted to mention. I know for some students the homework is kind of a lot, but I would encourage you to be sure to finish it up, even if it's after it's been due. If you miss the due date, it's not the end of the world. You can still get most of the credit. So the real main reason for having the due dates is just to make sure that we don't get behind. So if you have a lot going on some particular week, that doesn't mean like, oh, I guess I won't do the homework that week. It means, come back to it, get it finished up. And like I said, you can recoup most of the credit because, uh, I mean, the online stuff has its disadvantages, but um, the the homework system is one of the better tools that we have. So I would really encourage you to make sure and get that stuff wrapped up. If you missed an assignment or something. Um, let's see. Uh, so like I mentioned with regards to gravity, there'll be a quiz coming, but probably in a week or so. Um, And then one other sort of administrative issue that I have on my radar is the final, what we're going to do with the final. There's been discussions, it may seem like sort of a long way off, but as you can tell, things are have been impacted, of course. Having quizzes seems to be reasonable a reasonable way to go about our sort of midterm assessments. I think it's nice because it kind of breaks it up into smaller pieces, and so it has spread out the worry about any of those not working very well. So I think we'll continue with that rather than having a big assessment now. We will do quizzes on smaller chunks of material. That way, if any one of them doesn't work as well because it's online, it's sort of it's less it's less the stakes are lower. But the final, I would still like to do some sort of comprehensive thing, and there's no way to really do that in terms of a quiz because you just can't cover enough stuff. So I've been talking to other faculty. It doesn't sound like there's especially great ways to do it, but we may do something that we do where we do it during the lab period that week. So, or we do some combination. Maybe we do some on the homework system, do some other, something. But I just wanted to let you know that I was thinking about that, and it may seem like a long way off, but we're halfway through the course already. So I will be sure to talk to you about that well in advance, whatever it is we decide to do. But I just wanted to let you know that that's on the radar. We'll come back to this, but that's kind of the other component in terms of assessment that we need to get figured out. Yeah, those are the administrative things that I wanted to mention. I'll be working on grading to get stuff updated for you, so you can see kind of exactly where you are because we are, about midway through the quarter. Yeah, do you guys have any questions about that? About administrative issues, etc.? Questions? Okay. Good. Let's see. Yeah, I haven't decided exactly. I think the compromise of having like a time limit um and like some window to do it in works fairly well. But some faculty have been talking about uh doing their final synchronously. So I haven't decided. But this would be a thing that I could get some input from you. So like, do you guys like what do you prefer actually? Um, so so I mean, one option would be we have it at a particular time, and then sort of the other option would be like what we've been doing with quizzes, where you have. Yeah. So that's the thing. We would do it during the lab time probably, because in theory that should be a time that's free for everybody. But this is one of my concerns as well. Um, is that people have other stuff going on. I mean, there's no guarantee that people are going to be free, etc. So that thus far I've been pretty hesitant to do like a test at a particular time. But a survey is a good idea. Yeah, that's an excellent idea. You can do that. Let me make a note of that to myself here. Yeah, those are good ideas. Other questions, concerns about administrative things, grading, etc., etc.? Okay. Anybody else? Are we awake? Ready to talk about work? Okay. Work. So, uh, this chapter is kind of interesting. Like a lot of terms in physics, work, we have sort of notions about what it is. Um, Doing work, right? It has a lot of colloquial associations. But we're going to give it a precise physics definition. And so I would say the word, work as a word has a lot of associations. We're going to nail down a precise physics understanding. Okay. Um, and this is in the next chapter, so chapter 7. Um, so the best way I think to define this is to give you a little bit of a picture. Imagine, let me draw this nice and straight. Imagine you have a surface, and so you can think of maybe our friction lab. You have a surface with an object on it, and let's say we pull on this object with some force, and that force is not necessarily, uh, you know, perpendicular or along the axes. And so this picture so far, this block has some mass, something like that, is sort of familiar. It makes us think of problems that we had done with Newton's laws. We could figure out the normal force. We could figure out the force along the surface, etc. Um, and the ingredient with that we're adding to this picture is, suppose that you succeed in moving it, the block. Okay. So let's say you move it from here to here. Okay. Um, and the force hasn't changed direction or anything. The definition of work, oh, we've moved it some distance d, is the force times d times cosine theta. So the cosine theta is selecting the component of the force that's directed along the direction that you've moved it. So in other words, it's the force times the distance, and it's the component of the force that's along the direction of motion. And we can actually write this as F dot D. Okay. So both force and, sorry, I should have said displacement are vectors. So another way to write this is, not a dot there, is F dot D, where this is the dot product. Have you seen this before, the dot product? Okay, so in Calc 3 it sounds like? Ah, okay, cool, cool, cool. Just working on it in Calc 3. So this is one of these concepts that's, okay, so y'all are in Calc 3. Okay. It's kind of tough because for students who are seeing it now, I think they will find this pretty straightforward, but not everybody is seeing it at the same time. So if you haven't seen this before, that's totally fine. You don't have to have seen this. We'll get you up to speed as to how to use it. But it's kind of neat for those who are seeing it now or who have seen it, that this is an idea that has application in physics. So I suspect you will probably run into example problems in calc where they're like you need to calculate the work and you use the dot product to do it. So that's good. So it sounds like it's familiar in Calc 3. Um, so the other thing I would mention is the units for this. So the units for work, force will have units of newtons, and this displacement will have units of meters. So the unit for work is the Newton meter, or kilogram uh, meter per second squared times meters, kilograms meter squared per second squared. This is the unit called a joule, J, and this is a unit for energy. So we will talk about energy in conjunction with work. So this chapter, the next chapter, and the unit for this is the joule. And this gets at this difference between scalars and vectors. So when we were talking about forces, you know, a force is always going to have a direction associated with it because it's a vector. But work is a scalar. So when we're talking about energy, it's just an amount of energy. The energy doesn't have any direction. So in other words, this is, now let me write this here. So kind of as a side note, this is a scalar, energy, but both force and distance or and displacement are vectors. Okay. So this gets at the fact that there are basically a couple math ideas. This chapter is sort of math heavy. For you, so you guys are in Calc 3, you'll have seen most of this already, but we'll take some time to kind of practice these math ideas because I know not everybody will have has seen them before. But there's two big math ideas in Chapter 7. So one is this dot product. And then the other is integration. So we have talked a little bit about integration with regards to, we used numerical integration to look at gravity. We've talked about integration with regards to kinematics, how you can relate things like distance to velocity and velocity to acceleration via integration. And if you all are in Calc 3, you'll have had some practice doing integration. So we'll come back to this. And for the time being, let's talk a little bit about the dot product. So I'm going to put this dot product in context of the fact that there are basically or so far we're talking about three different kinds of multiplication. So I'll call this a little bit of a math review aside. So just to give you some context on the dot product. So one kind of multiplication is if you have a scalar times a vector and you get out a vector. So this just changes the magnitude. So for example, we've done stuff like this already. You know that the force is proportional to the acceleration by mass, but mass does not have, it's not a vector, it's just a scalar, an amount. So this would be an example of sort of our regular idea of multiplication. The next kind of multiplication is what we're just talking about. You can get a vector times a vector, and you get out a scalar. So that's the current situation that we're talking about, work, where both. I'll put it like this. You know, this is a scalar, but this is a vector, and this is a vector. And then the third kind of multiplication that we'll hopefully get into is you can have a vector times a vector, and you get out a vector. And the example that hopefully we'll talk about some is torque. So and this is, so this was called the dot product. This vector times vector giving you a vector is called the cross product. So the dot product is just like it sounds. Usually use a dot to denote it. The cross product, you usually use, you know, kind of our X multiplication symbol. Have you guys encountered the cross product before? You run into the cross product? Okay, so I suspect you probably will get that later this semester in Calc 3. It's kind of a similar, it's a little more complicated to calculate than the dot product, but it's another example of vector multiplication. Ah, okay, okay. So it's coming. It's coming for you. The cross product. We're not going to talk about it at the moment because the applications of it are not until later. But if you're curious, one of the Lewin lectures talks about all three of these, or you know, it talks about dot products and cross products at the same time. We're going to kind of break it up because it fits better with the way our material is organized. But So we'll table this cross product for now, but we will do some work with the dot product today. Okay, so we'll come back to that, but let's go back to work. So let me give you some qualitative examples. Okay, so let me give you, I want to show you just so you can kind of see an object. So one example, I have a coffee cup right here. I am holding the coffee cup up. I'm holding it up, okay? This example, there's a force of gravity that's pointing down. There's the force that I'm exerting on the cup that's pointing up, but I'm just holding it. In this situation, there's no work because there's no distance, okay? Another situation would be I'm holding this cup. The force I'm exerting it on it is opposite its weight. It's holding it up. Now, if I move it sideways, okay, in this situation, the force that I'm exerting is pointed up, but the displacement is pointed sideways, so I'm doing no work in this situation either. Okay, so I'm holding it, moving it sideways. The other situation, though, would be if I'm holding it and then I lift it. In this case, the force is pointed up that I'm exerting, and the displacement is also up. They're in the same direction. So in that situation, I am doing work. So I think that example contains, it's nice to visualize an object when you're thinking about this. So that example contains a few different quick things that you can have kind of in mind as to what work is. So let me now just kind of catalog those examples that I was just showing you. So example 1, holding an object. So we have our coffee cup. So I'm doing no work in this situation. Okay. Question. Uh, yeah, so since they're both vectors, f and d, they have to be in the same direction. Uh, they have to be in the same direction for there to be work. Yeah. Yeah, so then we'll talk about how you look at the net work. So that would be you look at the sum of the forces. It's kind of an analogous, or it kind of builds on like net force. So we'll talk about that. Yep. You can. That's good. You can anticipate kind of where this is going. But so for this simplest example, if you're just imagine, you can have an object in front of you, holding that object. You're doing no work in that situation because there's no displacement. So kind of the next example that I just mentioned to you was Now if I take that and you move the cup sideways, now in this situation, the displacement is sideways, but the force that you're exerting is pointed up. So this is also work equals 0, because you can think of this as, because the dot product is going to give you 0, it may be easier to think of this as FD cosine theta and think that the angle between the force and the displacement is 90 degrees, and cosine of 90 degrees. So like, let me just draw a picture like this. If this is 90 degrees, then cosine of 90 degrees is 0. And so the work is going to be 0. And then kind of this third example that I was showing you. Now, let me give myself a little more room. Now, if we lift it up, or let me call it lifting force this time. In this situation, the work is not 0 because the force F dot D is not equal 0 because the force and the displacement are in the same direction. So in other words, if they're parallel, like this, parallel, then the cosine of 0 degrees would be 1. And so this would just be the force times the distance, or the displacement. And in fact, we could figure out what this is. So if you're holding this cup, you know that the size of that force is going to be basically the weight. So the force that I am doing on the cup would look like mgd. Let me give this a subscript. Or a description here. Now, we can add to this picture sort of something that's kind of confusing is, notice there's another force that's in this picture that is not perpendicular to our displacement, and that is the force of gravity on the cup. So it turns out the force of gravity is also doing work on the cup. So for that part, think of this as, the force of gravity is pointing down, but our displacement is pointing up. So you can analyze this in the exact same way, except now the cosine of our angle, instead of it being 0 degrees, you can think of this as being 180 degrees. And what's the cosine of 180 degrees? Yeah, exactly. So if we look at the work gravity is doing on the cup, it's going to be negative mgd. So, like I said, you can think of this as either you're evaluating the cosine, or you can look at the picture and see how of course, gravity is pointing down, our displacement is pointing up. Since it's going, in the opposite direction as the force, you know that that's going to be a negative quantity. So these examples of like lifting an object, uh, holding an object, and walking with it are sort of kind of the most basic qualitative examples in terms of calculating work. So let me, or are there questions about that so far? Let's see. Is it F in the bottom cup equal to mg of the top cup? Yeah, yeah. So it's a little bit contrived, but the picture, are you talking about like here? So yeah, we could think of, as long as it's not accelerating, like if you were lifting it up at constant speed, then the sum of the forces in y, to connect with our previous conversations about this sort of thing, you would have, the force lifting minus mg would equal mass times acceleration. Provided it's constant at constant velocity, then this would be 0. So in other words, the lifting force would have the same size as mg. So that's why we talk about it here as the work I am doing is mgd, because my lifting force is the same size as mg. I mean, granted, there's going to be an instant where it goes from stationary to starting to move where it's accelerating, and then that wouldn't apply in that case. But for the majority, if you kind of think of the simplified picture of it's moving at a constant speed, which is reasonable for, most of the duration of your moving it. But yeah, that's a good question. Um, Other questions? So let me show you an example that's not perpendicular or parallel. Um, so the example that I want you to consider is, suppose, so it's kind of a little bit of a contrived example, but um, consider a hiker. So this example is in your textbook too. So 7-2. Um, consider a hiker that is hiking up some hill. So sure, the hill is not actually this triangular, but you see what I mean. They're hiking up some hill that has a height of 10 meters. Um, so they're exerting a force along this, this arrow, more or less. And this is a little bit weird because we're so accustomed to thinking of our angles as being, relative to the x-axis. But really, we're interested in the component of the force that is along the height. So you can think of that as being this angle, or alternatively, it would be this angle. If we think of the height as a vector, yeah? So actually, let me put this in a different color just so you can see it distinguish here. So I put the height in blue, the force in blue, and the height is still in black. And the question is, we're going to imagine that they have a backpack, okay? And that backpack has a mass of 15 kilograms. And we're going to assume, like I mentioned above with my example with the coffee cup, that this hiker is moving at constant velocity. So the question is, how much work does the hiker do on the backpack? Um, so let me redraw our picture just in terms of the vectors that we have. And you can kind of see why I put theta where I did, because we know that the definition of work is going to be the dot product FD cosine of the angle between them. Um, okay. So notice this d cosine theta if you look at this. Oh wait, I have these. Sorry, I have this switched around. Um, so the force is along an angle, and D is along there as well, and H would be just upright. Yeah, sorry, I mislabeled that. So notice this D cosine theta. What is that? Oh, I made a mistake. I made a mistake. Wait a second. So this gives me this is a learning moment for me. Here, look, I rushed ahead with my picture, and because of that, I neglected something. So let me uh, redraw our picture here with the guy with the backpack. The thing that we should do is always make sure to draw a free body diagram. So if I draw a free body diagram, we have the weight of the backpack pulling down. The force that the hiker is going to have to put on the backpack to hold it up would just be opposite the weight. Okay? So the way I have this drawn here is not correct. The force is not at an angle. That's just the displacement. I was looking at my notes here and I was like, why? Wait, what is going on here? Because we need the angle between the force and the displacement, and the force is just pointing up, and the displacement is at an angle. Okay? So, and that becomes clear when you look at your free body diagram. So, the reminder to myself as well. So sorry, that was sort of injecting a little bit of confusion. That's on me. Um, so always give yourself a free body diagram to track down which forces, the directions of forces and stuff. And, whoops, like with our coffee cup example, this was really helpful for figuring out what direction the force was relative to our displacement vector. It's the same situation here. So the force is pointed up. Okay, so this d cosine theta, what is d cosine theta? D cosine theta is just the part of the displacement that is vertical. So you can think of this as being h. The force, we can sum the forces in the y direction. The force of the hiker is pointing up. mg is pointing down. Those are going to sum to 0 because it's not accelerating. So the force of the hiker is just mg. So we put that in here. We'd have mg times the height. We could then calculate this with some numbers. The mass that we had was 15 kilograms. We know gravity is 9.8 meters per second squared. The height in our picture was 10 meters. So if we multiply these things together, we get 1470 joules. So, and this is the work the hiker does on the backpack. Okay. So, and I don't want to I got turned around there for a second. I'm not going to overrun our time just a minute here. So the analogous thing would be just like we did with the coffee cup, the work gravity does on the bag. So, and we can get this from our picture. The displacement was like this. Unlike the force of the hiker pointing up, the force of gravity points down. So you can see this angle, the angle between them, is bigger than 90 degrees. So this is going to be negative. So this, just like we talked about with the coffee cup example, so this would be negative work. MGH, but negative. Negative 1470 joules. And then the other thing that I would mention is, what's the net work? Net meaning total. And this is sort of foreshadowing some of the sections that are coming up. But if we look at the net work, the work that the hiker does plus the work that gravity is doing, we see that that's 1470 minus 1470. It's 0. So the net work is 0. And we're going to connect that with the concept of kinetic energy in a section that's coming up in a couple sections. But this gives you an example of a question, despite my kind of injecting with some confusion with which direction our force was pointing. If you know the direction of the force, and you know the displacement, and you know the angle between them, you can calculate the work. It's trivial in situations where they're pointed in the same direction, or where they're perpendicular, or where they're anti-parallel. And for situations where those things are directed at an angle, you just need to evaluate the cosine theta. So we kind of cheated a little bit because we could recognize in our picture that the displacement cosine theta is the same thing as the height in this scenario. But you can see, and we'll do some more examples with this. So next time we'll talk a little more about the dot product. We'll look at some more example problems. We'll start to get into forces that are not constant as well. And that's where we're going to talk about integration. But yeah, that's a real quick introduction to work. Transitioning from talking about forces to talking about energy. Work is kind of the connection between them. Questions. I'll try and be better about your time here. So give you a break between your courses if you have a course at 9. Questions? Yeah, so we used the angle, but it was sort of a really simple. Oh, you're talking about here with regards to gravity? Ah, yeah. So the antiderivative. Yeah, in other words, if you have a force that varies, you need to integrate F dot D. So, and then another word for integrate is antiderivative. Yeah, so we didn't use the angle here because it was the same as in the first part. It's just that it's negative. So maybe a better way to draw this card. is that the height, so let me put it to you this way. The height is the same. It's just that the sign has flipped. Sure. Yeah, there's different ways to think about. It's kind of weird, or it's a little bit. I think it's a little bit unfamiliar sometimes to think about angles that are larger than 90 degrees. But yeah, you could think about it as adding 90 degrees or something like that. We'll look at we'll look at some more examples where we make more explicit use of the angle, and I think that that will clarify that. I think a good way to think about it with regards to this problem is that, it's not like the height has changed. So it's not going to be between, uh, a value other than 1470. It's just going to make that value negative because it's gone from exactly pointed up to exactly pointed down. Other questions? Those are good questions. Okay, I want to give you a couple minutes to get to your next obligation if you have one. So sorry for bleeding over. Man, it's tough online to avoid. Um, if you have other questions, let me know. Shoot me an email or post on Teams and we can talk about it. We'll look at some more example problems next time. Um, yeah, I think a good thing to keep track of is if you're between 90 and 180 degrees, or really uh, between negative 90 and negative 180 degrees, that whole half of the space is going to be negative. You can imagine a cartoon. What is going on here? Well, my pen is not working for us. Huh. I was going to draw in there, but it's not working. Um, yeah. That half of the coordinate plane is going to yield negative work. Well, now it's drawing. If your force is pointed in this direction, if your D is, or if that angle is anywhere over there, then it's going to be negative. Okay, well, thanks for your attention. We will see you soon.